Okay, so let's suppose that we have a ramp, alright? So on top of the ramp, we have two objects. One is a ring, well, it's just a ring with mass m, and the second object is a disk, alright, solid disk also with mass m. So actually, let me just write that here. So a ring has mass m, radius r, and this disk here has mass m, radius r. So basically, a ring and a disk, same mass, same size, okay? So what we do is, on top of the ramp, right, we hold both objects at the same position, right, both at the top, both the ring and the mass, and then we let them both go. And the question is, which one hits the ground first? So you might think that because both the ring and the solid disk have the same mass, they'll both hit the bottom first. No, both hit the bottom at the same time, right? Or you might think that because the acceleration of gravity is the same for both, right, 9.81 meters per second squared, angle's the same, all that, it's the same incline. Because of that, you might also think that they'll both hit the bottom at the same time. But what I'm here to tell you is, it's actually going to be the solid disk that hits the bottom first. And the reason for that is something called moment of inertia. So let me just, I'll write the formula for moment of inertia of both these objects, and I'll explain what moment of inertia is. So moment of inertia, we'll call it I, because I for inertia of the disk. So ID is going to be equal to 1/2 mr squared. But the moment of inertia I of our ring, so IR, is equal to mr squared. So you can see here that with the same mass and same size, the moment of inertia of the disk is going to be smaller than the moment of inertia of the ring. Because here we have multiplication by 1/2, and here we have multiplication by 1. And for a bunch of other objects, there are like tables of moment of inertias for those kind of objects. But I just wrote them here for disk and ring, because that's what we're talking about. So what does this mean? What does the fact that the moment of inertia of the disk being smaller than the ring have anything to do with stuff rolling down ramps? Well, the moment of inertia basically measures how hard it is to, how physically hard it is to rotate something. So the moment of inertia of a disk being smaller than the ring, it means that it's physically easier to rotate the disk than it is to rotate the ring. And since we're rolling two objects down a ramp, well, rolling implies rotation, so it's harder to rotate the disk than it is to rotate the ring. If it's harder to rotate the ring than it is to rotate the disk, well, it's going to be harder to get the ring going, right? It's going to be harder for the ring to get moving, accelerate down the ramp and all that, than it is for the disk to get going and accelerate down the ramp. And because of that, well, since it's harder to rotate the ring than it is to rotate the disk is going to finish faster because, there's less resistance. You could think of it like that. It was just easier for the disk to get going, get down the ramp. So that's basically it, right? No friction. It's not because of friction. It's not because of air resistance. Not because of quantum tunneling or whatever. Simple moment of inertia, right? So you would think that they'd both hit the bottom at the same time, but moment of inertia says otherwise. That is why the disk reaches the bottom first. So pretty interesting, really. Found this interesting? Feel free to like. If you didn't find this interesting, well, I don't know. You can decide what to do. If I made any mistakes, put it down in the comments. If you want to comment on anything in general, see what I can do better, or comment on what I can do better, just put that down in the comments. So pretty cool stuff. I'll see you in the next video.